In today's video, we shall look at a few problems on static equilibrium. Let's look at problem 1. A meter stick balances horizontally on a support at 50 cm mark. What that means is, if you have a meter stick like this, when we say meter stick, this is marked 0 and that end is marked 1. So that is to denote the length of this meter stick is 1 meter. If it balances horizontally on a support at 50 cm mark, which means you can support or balance this meter stick exactly in the middle, 0.5 meter mark. What that means is the center of mass of this meter stick is exactly in the middle. So that is where the weight acts, like that. And the weight causes a normal force from the support onto the meter stick in an opposite direction, so they balance each other and they find a perfect equilibrium. Let's move on. A mass of 10 grams is placed at the 15 cm mark and the stick is found to balance at the 46 cm mark. What is the mass of the meter stick? What that means is, if you place, say, a mass here, the mass is 10 grams, and the mark or the point at which this mass is placed is 0.15 meter mark, like that. It is found that the balancing point moves slightly to the left, like that. So this is the 0.5 meter mark, and this point here denotes 0.46 meter mark, where the new balance point is. Based on this information, you are to find the mass of that meter stick. So let's do a free body diagram on this second diagram here. So the first is the weight of that 10 gram object. 10 gram is equivalent to 0.01 kg, which means the weight is 0.01 times gravity, and this is in the units of newtons. What other forces there are? You have the normal force from the support onto that meter stick, let's call it N, and then you have the original weight of that meter stick itself. We know the point at which it acts is exactly in the middle, namely at the 0.5 meter mark. So the weight of that ruler acts exactly at the middle mark of that meter stick. Let's call it the mass times gravity. This mass is what we want to determine. Remember, there are two conditions of static equilibrium. The first condition is the net force acting on this meter stick is 0. And condition 2 is the net torque about any point on that meter stick is also 0. Now, we don't have to use both of them to solve the problem. Sometimes it's sufficient to use just the first or the second. In this case, it is sufficient to use the second condition to solve this problem. We need to evaluate net torque about an appropriate point. Remember, we can choose any point. So the point that we want to choose here is about that support. So we let the axis of rotation to be there, because by choosing the axis of rotation at that point, we can eliminate the normal force from our equation, so we won't have an additional variable to deal with. Now all we have to do is to calculate the torque due to this force and that force about an axis passing through there. Let's do the torque due to that force. The force is 0.01 times gravity. The moment arm is that distance, the distance from the axis of rotation to where the force acts, and that distance is 0.46 minus 0.15. So 0.46 minus 0.15. Now you note that the moment arm vector is perpendicular to the force vector, so sine 90 is 1. You don't have to worry about anything else. The direction of this torque is coming out of the board, as you can verify using the right-hand rule. Now let's turn our attention to the second force, which is the weight of the meter stick. The torque due to the weight of the meter stick is the weight of the meter stick, mg, times that distance, the distance between the axis of rotation and the point where the force acts. In this case, it is 0.5, which is the point where the weight acts, minus 0.46, which is where the support or the axis of rotation is. And that is 0.04 meter. The direction of that moment arm, or the r vector, goes from axis to where the force acts, so rightward. So that is the vector r. The force is going downward. When you curl your right hand fingers from r to the force mg, your right hand thumb is going into the board. So the direction of that torque is into the board. If direction out of the board is taken to be positive, the direction into the board must be taken to be negative. So when you sum these two terms, you should get 0. G goes away, and the only unknown is the mass of the meter stick, which you can solve. When you do the calculation, you get the mass of the meter stick to be 0.0775 kg, or quite simply 77.5 grams. And that is the answer. Problem 2. A uniform sphere of mass 0.8 kg and radius 4 cm. So the radius is 4 cm, and the mass of this sphere is 0.8 kilograms. Is held in place by a massless rope, attached to a frictionless vertical wall at that point. The distance between the center of the sphere and the point of attach is 10 cm. Find the tension in that rope and also the force on the sphere from the wall at that point. So let's do the free body diagram. The first one is the weight of that sphere, which is vertically downward. Since the mass is 0.8 kg, the weight is that mass, 0.8 times gravitational acceleration. The second force is the tension in that string, T. And the third one is the force on the sphere from the wall, and it acts at 90-degree angle with respect to the wall, like that. We have to determine this and that. So let's determine the tension. As you will see, we can use condition 2 to determine tension. That means you have to figure out a point about which to calculate the torque. If you want to find a point to calculate the torque, that eliminates completely the force F so that it doesn't appear in our equation, then that must be the point. So we choose an axis through the point where the force F acts, as marked with a cross here. So we are using the second condition of static equilibrium to get our tension. Now there are two contributions to torque about that axis. One is from the tension and the other one from the weight. So let's do the weight first. The torque due to the weight is the weight, 0.8 times gravity, times the perpendicular distance from the force to the axis of rotation. So in this case, that distance is that, which is equivalent to the radius of that sphere. So that means 4 cm or 0.04 meter. The angle between them is 90 degrees, so sine 90 is 1, and that's it. The direction of the torque, remember the vector r is going to the left, like that. Weight is going this way. When you curl your fingers from the vector r to the force, like that, right hand thumb is pointing out of the plane, so the direction is out of the plane. Now let's calculate the torque contributed by that tension. So the force is the tension itself. The perpendicular distance between the point where the force acts, the tension in this case, and the axis of rotation is again 4 cm or 0.04 meter. Remember, we are calculating the torque, which is essentially a cross product. The magnitude of it is the magnitude of r times the magnitude of F, which is T, and 0.04 times the angle between them. So in this case, the angle between them is that angle, theta. Let's for now write sine theta there. The r vector is going this way, tension is, though the force is going that way, so the direction of the torque is going into the board. So if this is plus, this is minus, so the sum is 0. Now let's calculate theta. Now we have a right angle triangle, so this is a 10 cm length. We are talking about this triangle right there. This is theta, this is 90 degrees, and this is 4 cm. So theta is arctangent of 10 over 4, which is about 68.2 degrees. Putting the 68.2 degrees inside this theta there, you can solve for the tension. And when you do that, you find that the tension is 8.45 newtons. Part B, this force F there. Now this you can use the first condition of static equilibrium to solve it. What that means is you consider all the forces that is acting along the x-axis or along the horizontal direction. There are two. One is the force F itself, which is going to the right, and the other one is the x component or the horizontal component of the tension, which is going to the left. So if the rightward direction is plus, the leftward direction can be taken to be minus. The horizontal component of that tension is T cosine theta. Weight of that sphere is vertically downward, so that does not contribute. So the sum is 0. You know the tension, so you can determine the force. Remember, theta is 68.2 degrees, and if you do the calculation, you get following result for the force: 3.14 newtons. And that solves the problem. So this is an example where both the static equilibrium condition can be used to solve the problem. Problem 3. A rope of negligible mass is stretched horizontally between two supports that are 3.5 meters apart. When an object of weight 3200 newtons is hung at the center of the rope is observed to sag by 40 centimeters. Find the tension in the rope. So you have a couple of points. The distance between them is 3.5 meters apart, and you have a rope that is stretched horizontally like that. When you hang an object exactly in the middle, whose weight is that, what happens is that the rope is observed to sag by 40 cm. So this is where the weight is. We want to determine the tension in the rope. So let's do the free body diagram for that object. So its weight is 3,200 newtons, and you have one tension there and one tension there. They are of equal value because they belong to the same rope. Now we can take this angle, say, to be alpha, so that is also alpha by symmetry. Now let's not forget that this distance right there is 40 cm, or 0.4 meter. That's that. Basically what that means is you have a right angle triangle, so this is 0.4 meter. This is 3.5 divided by 2, so 1.75 meters. That is that point, that length right there, and that is alpha. So alpha can be determined immediately. It is arctangent of 0.4 over 1.75. To solve this problem, it is sufficient to look at just the first condition of equilibrium. In other words, we look at the net force along the y or the vertical direction and equate that to 0. So there is this 3200 that is along a downward direction. The upward direction forces are contributed by two terms. One is the vertical component of that tension, another one is the vertical component of that tension. Let's go back to this diagram. The tension is this way. We want to determine the component Ty of that tension. In terms of alpha, Ty is T sine alpha. Note there are two terms, so 2T sine alpha. Alpha can be determined from this equation, which gives you 12.88 degrees. Putting that in here, we can solve for the tension. When you do that, you get the following result for the tension: 7,178 newtons. And that solves the problem. Thank you for watching.